चाहिँ तपाईको
दण्ड
कम्प्युटरमा गरे नि त्यो क्लाउड रेकर्डिङमा
कम्प्युटरमै गर्ने
कम्प्युटरमै गर्ने हजुर अलि क्लाउडमा त स्टोरेज अलिकति प्रब्लम भइरहेछ हुन्छ
दण्ड चाहिँ म फेसबुकको लागि तयारी गरौँ
हुन्छ
ओके सिरिज
हुन्छ स्टार्ट गर्दा हुन्छ अहिले
हजुर मेरो
हुन्छ हुन्छ
Yeah, we're live now.
Hello all, good evening, good morning, and good afternoon from all the time zones. I would like to welcome you to our 6th GIIS webinar series, AI and Emerging Technology for Sustainable Future. I am Siris Marjan, a research associate at GIIS. So before we begin our program and begin our session with our guest speaker, I would like to speak something about our organization and this webinar series. The Global Institute of Interdisciplinary Studies is an independent, non-for-profit, and a research-based institution based in Kathmandu, Nepal. This has been providing and doing lots of interdisciplinary studies, which produces a very salient and information knowledge, which is used for the catalyze the transformation policies of Nepal and elsewhere. The AI and Emerging for Sustainable Future is a research-based group at GIIS, which is used to do research on the very emerging technologies such as data science, machine learning, cryptocurrency, augmented reality, and many more. Over the last few sessions, we had very amazing speakers with us, in which they shared their ideas, they presented their thoughts, and they shared lots of their work with us. So today, I would like to welcome Dr. Danda Pani Paudel ji to our webinar series. So talking about our guest speaker, Danda Pani Paudel ji has completed his PhD from the University of Burgundy, France. He is also a postdoctoral researcher at the computer vision at ETH Zurich, Switzerland. His main area of interest includes computer vision, unsupervised machine learning, and robotics. Today, he will speak more about more about deep generative models, the promises and danger, how the deep generative models and how it has causes the pros and cons of deep generative models. He will mainly focus his idea on the images and videos which we share in our daily life. And he will also share about the deep generative models and the deep video manipulation such as deepfakes, which is used for fraud, misleading, misinformation, and many more. So regarding on his professional career, he has done many projects on computer vision in his last year. He is also a co-founder. He's also a co-founder and a very active member of NAMI Nepal, which is also an AI and informative-based research institute based in Kathmandu, Nepal. So without a further ado, I would like to welcome and give the stage to our chief guest for tonight, a chief speaker for tonight, Dr. Danda Pani Paudel. All yours.
Thank you, Siris, for a nice introduction, and thanks, Jis, for providing this nice opportunity. So today I'll be talking about deep generative models, promises and dangers, and I would like to welcome you with this familiar voice. Let me know if you cannot hear.
Welcome to the GIIS webinar series.
That's supposed to be, if you could hear the voice, that's supposed to be Donald Trump welcoming you to this webinar series. And that's generated, of course, by an AI. All right. So until 2 years back, I used to present this particular slide, still from 2 years back, actually. And then the question is basically looking at these 8 different images and finding out which one is actually the real image and which actually is the one generated by AI. And you can make a guess. I'm going to reveal the answer that these crosses are actually the fake generated by AI, and these checks are actually the real images. Well, you in a first glance, it might be quite difficult to know which one is real and which one is fake, but if you have a closer look of those images from 2 years back, you can see different kind of artifacts from the here on the here you can see that the text you cannot read at the background. Similarly, the background is kind of surreal, and here you can see that the symmetry is not maintained, and the eye symmetry is not maintained, symmetry in the ears are not maintained, and so on and so forth. You can see that teeth is actually not that great, and hair is quite messy, and then even the gender is quite non-stereotypical. So this is how you could know if an image is generated by an AI or actually it's real image. Then 1 year down the line, this is the other result that you may try to guess which one is real and which one is fake, and then all of them, they happen to be fake. It means that the problem that I mentioned just before are not there anymore, and it's very, very difficult to know it is real image or fake image, and that's how good AIs are on generating images. But now the time has changed, because the images that I'm bringing today is about the real and fake again, and these are the image patches, and I would like you to pay close attention to figure out which might be the real image patches and fake image patches. These are the real images patches, and these are the fake image patches. It may not look so surprising for you now, but if you know that these are the images being generated without even given the real image examples. So AI learns not by even by looking at the images. Previous images, the fake images that we have seen, those actually are generated by looking many images, whereas these fake images actually are generated without even looking at any real image. This is purely synthetic image-based generations. So the question is, why do we generate images? And from the computer vision point of view, that we want to understand images, and then Richard Feynman famously said that what I cannot create, I do not understand. It means that to understand the image content and image itself, that we need to, or it seems promising that that being able to generate images would also allow us to understand these images. So it's both the sides. One side is of course just to generate, and the other side is also to understand. Well, in today's talk, we will be talking about generative adversarial networks. These are the generative models that they play at the adversarial game to generate images, and we'll be focusing mostly on images and part of the audio maybe later. That in short, generative adversarial networks, I will be naming them GAN or GANs in plural. And GAN, basically they predict data given a label instead of label given a data. You can see here that if you want to generate an image of a cat, then you ask for a cat and you generate a bunch of images of cat using a network, which I call generator G. This generator G is trained in an adversarial manner, and that adversarial manner, generative adversarial network, basically learns by playing this min-max game, more like in chore police style, where generator G tries to generate images which are as close as possible to real images, such that discriminator D, which is trying to differentiate whether this is real image or fake image, will know, we will learn to know that whether this is real image or fake image, whereas generator G generates this particular image and try to fool the discriminator. This is really one is trying to catch the generator, whereas generator is trying to fool the discriminator. This is how the game of the adversary takes place. And hence these images at the end, the generator alone would suffice to generate the real looking images purely based upon the noise as an input once this has been trained. And hence this is how the images are generated. Here generator G and discriminator J are two players. You can think as a two-player game that these two players are playing this game, so-called the min-max game, and one is trying to minimize the maximum game of the other. So discriminator is trying to catch, the generator is actually discriminator trying to minimize the maximum game of the other. It means that if one wins or the other loses, a standard winning and losing game, so which is also called the zero-sum game, that if one wins, the other loses. John von Neumann, very famous scientist from 20th century, he famously said that as far as I can see, there could be no theory of games without that theorem. I thought there was nothing worth publishing until the min-max theorem was proved. It means this particular game of doing this two generator and discriminator playing this game of one is trying to fool the other and the other is trying to catch. The first is basically becomes a min-max game, and I give you quick examples how these min-max games actually play. Here, blue and red, there are two players. Blue player can have three choices, A, B, and C. Similarly, red player can have two choices. The numbers in the box, it means that in this particular box, let's say that if blue makes choice C and red makes choice 2, then blue wins 20. At the same time, red loses 20. Therefore, this is zero-sum game. On the other hand, if blue makes choice A and red makes choice 1, then the red wins 30, whereas blue loses 30. If you start the game from somewhere here, let's say, then here the blue has made choice C already, and then red has made choice 2. Then if the red is allowed to make a choice, different choice, then it's clearly advantageous that red would instead go for choice 1, so that red can win 20, whereas the blue loses 20. If we continue playing this game, then the blue would now rather choose to go from C to B so that it can still gain 10 while red losing 10. And similarly, if you can continue this game, and then they will take one of the player will take one actions, and then that would dictate the action of the other player, and then they will play this game of the adversary. This exactly the game of the adversary is actually playing between the generator and discriminator, where generator is trying to fool the discriminator, whereas the discriminator is trying to catch the generator, and that's how these networks are trained. And you can see that here your generator is trying to so generator is trying to minimize the maximum gain of discriminator. You can see also the other around, that the discriminator is trying to minimize the maximum gain of the generator. And Jan LeCun, who won recent Turing Award, and is also very famous for its convolutional neural networks, has said in a conference that generative adversarial network is the most interesting idea in the last 10 years in machine learning. And actually, the idea of learning using this adversary has been explored since 1959, but this particular one, the one made famous was since 2014. In today's talk, we'll be looking into two streams of these generative models, and so that we can really start from the basics and give the glimpse and the idea about that, how these deepfakes are generated, how things are modified, what all can be done. And I'll also give you some examples and then maybe some pointers where you can find more information. This in the first stream of this talk will be about just generating purely the images, whereas the second stream of the talk will be about generating images, but still condition upon. It means that you know some kind of input, and then you want to somehow manipulate that input to generate new images. The other set of images from ImageNet, which is a quite famous image collections with the labels in quite broadly used in computer vision. And this will be the examples of the real images you can see. And the first one, the GAN was from Ian Goodfellow, and Ian Goodfellow and his friends were in a bar having a beer in the evening, and Ian Goldflow came up with this idea, and he goes back home in the evening after getting drunk, and then implements this particular networks in 4 hours and gets this particular results. And this becomes really the beginning of new era of adversarial learning, especially in deep learning setup. Here, basically, you can see that these are the neural networks being used. On this side, this is actually the noise. It's fed in as an input. This is a generator, and then you generate this image, and this is the discriminator, and that's how the discriminators and the generators actually will play this game in these setups. That the both generator and discriminators are actually the neural networks. This particular one has been enhanced by this particular GAN is very easy to implement, and I'm just showing you the examples that how generator and discriminator can actually be implemented, and how the loss could be implemented, and the whole training protocol can be written. So only these few lines of code, one can actually make the discriminator, generator, and train them. So if you are interested on doing deep learning and learning how to implement a generative adversarial network, is very, very simple. You will get plenty of tutorials, and I'm just showing a few examples here. I mean, by an example that there's just few lines of code written in PyTorch that you can easily learn in half a day or something, if you are familiar with PyTorch already or Python already. All right, so then the improvements in the GANs have been taken place using these inverted convolutions, or you can call this transverse convolutions. That this is just better architectures, and nowadays everybody use this kind of architectures with transverse convolutions. Similarly, more improvements have been made in terms of the loss, because the training GANs they happen to be not that easy, and then those can be trained better by using better loss functions. And often, if you are training your GANs, you often end up using something called Wasserstein GANs, Wasserstein distance. Basically, it's the images of the real images and fake images will be seen as more of a distributions, and you're trying to probability distributions, you're trying to align these probability distributions by computing the distance between these two distributions. In this process, the expectation of these two distributions are brought together by using the Wasserstein distance, Wasserstein loss, basically. And more improvements have been made by doing this progressive learning, because you, just like the babies learn gradually, or students learn gradually, but easier things first and then more and more difficult things later on. You can also call that the continual learning, and that's kind of process has been mimicked inside these deep neural networks to first generate this kind of blobby images of only 4x4. You just train a small network and try to generate this kind of very coarse images, and then after that you add the new layers and train them separately, and then try to enhance these particular images more and more, and make them higher and higher resolutions. So the training protocol basically takes going from low resolution to high resolutions in a progressive manner, and that's what it called the progressive GAN. And this progressive GAN actually one of the breakthrough in generating images, in a very, very realistic manner. So this is actually the other set of the images that I showed you in the very beginning, that how you could actually catch whether it's the real image or generated by the AI. So this particular AI, it's trained using Wasserstein laws. It's trained using adversarial manner, and then it is trained in a progressive manner of just going from low resolution to high resolution. So the state of the art GANs, though, it's called style GAN, where it injects these style noise layer wise. It's more sophisticated architectures than the progressive GAN, but that's more of the details about how these GANs take the noise as an input and manipulate it within the architectures. But those things are also not that big of deal to understand. I will spare the details for now, but the general idea, you can see that. So generally the traditional kind of GANs have this noise as an input, and then you have this standard blockwise architectures to generate the images, whereas the style-based generators will map the noise into different label of the styles, and hence translate this translate this noise to generate the images. The images generated by style GANs are so good that you can more or less say that it was 2019, and from there on there have been no research on this particular direction, because it seems like the problem has been solved on generating very, very realistic images. You can see here that the images of these bedrooms and images of the cars, given lots of images to learn from, the style GAN does a really good job, to the point that you not even be able to differentiate whether it's generated by AI or actually it's the real image. Here are more images generated by style GAN. You can see all the details that look super duper good, including the background, foreground, and the skin color to everything, all the facial details. So that exists the interface where you can actually play with your input parameters to generate different kind of faces that you wish to generate. Here you can see that the user is interacting with the different parameters, which is the input to the style GAN, and then the output image has been changed accordingly. You can see small changes only making small differences in between the images. Actually, style GAN has been integrated in a web page. It's called this person does not exist. Here's the link. If I click into this, you find this particular image of this person generated by an AI using the style GAN architecture, style GAN v2, that this person just doesn't exist. And you can basically keep on refreshing these images. You can find this very, very realistic face images, and none of this person actually exists. These are all the images that's generated by the style GAN v2. Okay, so all right, so that was the story so far about just generating images from noise. But what if you want to control the images, where Z is the noise here, and then Y is some kind of input, which could be a label, or which could even be the image itself. And then rest remains more or less the same. It's more about you have got two inputs now. Therefore, the image manipulation should take in this particular form, or even generating cats or generating dogs, differentiating them would take in this particular form. Here you can see that if you are starting from a sketch, and if you want to make a real image of this sketch, then you can exactly train in this particular manner. This was the paper in 2017, it's called Pix to Pix, that actually translate your sketch into the real images. This more or less becomes the same as I discussed before about generator and discriminator, where the input in this time not only the noise, but is also this case. Actually, if you see the Google Maps, then you can see in two different forms, right? That this is the satellite view and this is the map, and you can actually convert the satellite view into sorry, the map into satellite view or satellite view into the map. So this is really converting different kind of images from one style to the other style, you can say. But then often you don't really have these kind of pairs between that this boot and this particular boot. They are actually paired together. This map and this satellite image, they are paired together. Therefore, it's easy to learn from them. Whereas often that is not the case. If you don't have the case, then you can actually even take this particular architecture is called CycleGAN. I will not go too much of the details. It's more about that. You can even learn to translate zebras into horse here, for example, just by saying this is the zebra, this is the horse. Now make this. I mean, basically you can show lots of images of the zebra and lots of images of the horse, and then you can ask these zebra images to be converted into horse images, and these particular horse images converted into zebra images. And not only that, you can actually translate the style of the photos. You can actually go from Monet's painting into the real photo, and similarly, you can go for real photo to Monet's painting and other artists, of course. Likewise, you can translate the images from summer to winter, winter to summer. Basically, these are the different ways of doing this style transfer between the images, where the semantic content doesn't really change much, more about the style changes, and that for that you don't even really need to provide the pair of images, how they need to be translated. You just have to show a bunch of images. For example, a bunch of images of zebra and horse. If you just show it to the network, it automatically figures out how we want the images of the horse can be converted into the image of the zebra. Those are more of the general images, but if you want to do on the human faces, because human faces are often the most interesting things for image manipulation. And here you can see this input image can be converted into different kinds of attributes. This is the blonde hair, and then female gender, and more age, and the pale skin, and so on and so forth. That these are the input images can be converted into of different facial attributes. You can see here also that it can also be converted into different facial expression. This is the work that's been done in 2018. Since then, many things have been developed further, of course. And generally, the idea is that you can give you can take your generator here, and then you can take an input image, and you can ask that what particular emotions, let's say for the case emotions, so what particular attributes do you want? If you want person to wearing glasses, then actually that input image with the wearing glasses will be generated. The fake image will be that it will generate the images with the wearing glasses or blonde hair and so on and so forth. Similarly, the fake image will be fed into the discriminator, and discriminator not only looks at the image and says whether it's real or fake, it also checks that if the image is wearing the glasses or not, the face is wearing the glasses. And this is how it's been trained. It's more about that you can not only integrate input image, and you also can ask what you want to be modified, and this is that particular case of modifying the facial attributes, such as hair and skin colors or glasses or and gender and so on and so forth. This is how generally the images are modified in the conditional GAN setups, and in the similar conditional GAN setups that you can go beyond the faces. And then this particular example is about generating all this kind of realistic looking images by training a very giant model on ImageNet that can generate your 1,000 different classes of images very realistically using single model. Well, you could just ask that you want a dog, and then it just gives you a bunch of, it just gives you a dog. If you want a mushroom of a particular kind, it just gives you the mushroom, and so on and so forth. So in this case, you are feeding some noise to give the varieties of the output. At the same time, you're asking what particular class do you want as an output. This is what we mean by conditioning, that is conditioning upon the classes. This particular example is that you see that what this AI is actually learning inside is that here you can see that this is the fish and this is a dog. And then if you see inside what AI is doing is it actually learns to find some intermediate representations of between dog and fish that actually still looks like an animal. And this is quite interesting to see because it somehow learns to interpolate into the semantic label between the classes. So that was more about requesting what image do you want, and then this particular work of 2019 is called SPID. It's on conditioning upon your hand-drawn paintings or the semantics as an input, and it generates beautiful images of the landscapes on others too, that based upon what semantics do you want at what location of your image. Here you can see on top, these are basically the semantics drawn by human, and then here these are the images generated that comply with these semantics. I guess this will be basically in this particular settings that you have the semantic as an input, semantic as well as the noise as an input, and then it generates the images that you want. I guess it will be more clear by watching into this video.
Our interactive application looks like a simple paint app. However, instead of color palette, we have semantic palette. Let's pick a label and use the fill mode to replace cloud with ocean. Some cliff rock will be nice. Let me make the scene more interesting by adding a small rock and a faraway mountain. You can apply different styles to the image by regenerating the style code or by stealing styles from guide images. We continue drawing by adding a small beach. Trying different styles or trying different semantics. It's all up to you. This time, let's draw some mountains and trees. I first draw a grass-covered hill in the foreground, and then mountain in the back. More cloud will be nice. How about we plant a tree on the hill, like this? Note that the same distinct objects, the trunk and the leaves of the tree. Now let's change the season. Even though we simply replaced grass with snow, our image generator did more than that. The tree leaves are gone, and there's now snow in the back mountain.
All right, so you can see that we can basically condition upon the semantics, just hand drawn that what you want, and eventually it generates the very beautiful paint that it's for everybody's use who are not especially gifted with painting with very accurate depictions. Then can be very useful.
Our interactive application looks like a simple paint.
So then the last work I'm discussing in the conditioning setups is it's using this single image based generations, where the idea is that you can use just a single image to generate multiple images or animate those single images. So even the training process, it takes no more than one image to train everything all together, and the results it can achieve are quite fascinating. That's here you can see that this is the single training image, and the network AI automatically learns and then make kind of GIF out of it. It knows that how things can move. This is also training image here, and then it learns to move these things, and AI has never seen anything more than one image. It's not even trained on big data set. And single gives the effect of this somehow. The wind is blowing on the tree. And my favorite is there is like some this kind of lightning going on and some fire on that's just taking place. Just based on one image, it can generate multiple images that can give you the video effect. Those are more of the state of the art generative models. And then I will also quickly discuss about the recent developments on some of the works that have been involved on what these GANs can do. And this basically is similar to the big GAN that I discussed before. It still generate the images that you wish to generate, but using much more less data. That is been done by learning to, intuitively speaking, learning to translate or establish relations between this panda and the bear. If you want to make a image of a panda, then it's enough to see most of the images of the bear and only very few images of the panda, so that the panda actually the relationship between panda and the bear is established, and hence the panda can be generated using very few examples of the images. Here you can see that this is how the transition would take place, and hence the AI will automatically learn that how different animals or different images are actually related, so that learning done from one particular data sets can actually be used to transfer into these new cases where the training data sets is very few, and you can learn from very few examples. On the other side of manipulating the human emotions, if you ask people to label the human emotions, it's not easy but to label all the emotions, because it's just difficult on defining them. Therefore, one can define that, okay, somebody looks angry, somebody looks happy, surprised, fearful, distressed, and sad, so on and so forth. But if people often they possess very complex emotions, and those complex emotions can also be generated and using the conditional GAN framework all over again, where the AI has only shown bunch of images and never told that what kind of complex emotion this particular person has. But then you can actually control those emotions and generate from single image varieties of rich expressions of the emotions. You can see here that this particular baby has like very subtle changes in the emotions that can be taken control. And here I could show you this image is how the such subtle changes in these expressions can actually be generated from the single image. Yeah, this is how from the single images different emotions can be manipulated. And not only that, images can also be generated by describing by the sentences. You can see that an armchair in the shape of the avocado. It's basically still condition up. This time is condition upon the text, and then then it has never seen the AI has never seen anything like this, because it doesn't even exist. But it can understand this particular concept and learns to generate this kind of images. You can actually go to this Open AI page, and then this is called DALI, creating images from text. And here, if you are asking for an illustration of a baby Dagon radish in a tutu walking a dog, and you can get a bunch of images generated by AI. They are quite realistic, actually. So here you see the exact same teapot on the top with GPT written on it at the bottom. So basically it can even understand the text and learn to write the text and so on and so on. So these are the results obtained by the model trained by OpenAI, and the model hasn't been released because of these privacy reasons that people may abuse them, but the results obtained by this model, they seem to be fascinatingly good. One more example about a professional high quality illustration of a giraffe turtle that that just you can describe in the text, and it learns, it generates in accordingly for you. That's also the part of this conditional GIIS, where you condition upon the text and then you generate images. And the last but not the least that I wanted to discuss about, that these are the images that's been generated on actually this visualization of the feature inside. It's called Deep Dream. That's been generated without even seeing the real images, and they look quite fascinating and full of colors and patterns. These all 3-4 works I just presented are quite recent works, and that's where the research is more focused towards getting this varieties of the generations without the images, with the text, and with very few amount of data, and then and varieties in terms of the complexity and details of the image generations. That's the research directions that's currently being explored in this image generation community. So as I promised in my title, that I'll be just talking about the promises and then the dangers of these kind of generative models. That so far I presented about 2 streams of the generative models. One is about the unconditional, one is about conditional. Unconditional was more for just to put in the perspective, and most of the conditional generations will offer you both the, or seem to offer both the promises and the dangers. So one of the promise that the conditional image generations offer us is to get better images than what you have captured. Basically, you can take a bad quality images from a smartphone and try to enhance them by using the generative models so that they look like the images that are taken from a DSLR. Here on top, you can see that they are not really good before you process them, and then you can actually translate them to make them look them better by adjusting a right color, right contrast, and minimizing the noise, and basically just doing this idea of the image enhancement. You can actually enhance your image such that even your bad senses can capture or can give you very pleasing images. This is basically comes down to from really going from this real images of not so good to real images that are good, and you can actually do this kind of translation of bad quality images to the good quality images. And that again done by using this conditional GAN, where the generation has been conditioned upon this bad quality images. There are more results, more close-up looks, and in one particular setting, let's say that this is the input image, and you can, if you compare but between these two, this is, let's say, one of the final method. You can see that in terms of color and contrast, this is clearly better. But not only that, if you just zoom into this particular small regions of the window, you can see that this actually captures quite good, wireframe here, unlike the existing method before. It means they've been constantly keeping improving over time. Those are regarding the image enhancement, and you can actually also use GANs to super resolution images. That means that you can start with the low resolution images, and you can bring it to the high resolution by just passing through a network and then supervising it accordingly. And you can see that this is some image of the low quality, and if you wish to have, well, if you give the image of low quality, you wish to have something like in this particular batch, something like these much of details. And if you just do traditional way of the interpolations and super resolute, it doesn't do good job. Whereas if you use the GAN-based methods, which is basically conditioned upon the low resolution images, and it can actually generate you a very high resolution shape. This particular output is quite close to this one. So it means that you can actually capture not only the better image in terms of the color and the contrast, but you also can capture better images in terms of the resolution by using this kind of methods. Once you capture bigger images, you also need to compress them. Then even in the compressions, this kind of generative models can be used. If you use traditional compression on the right here, that with the same compression ratio, it means how much small file, same file size, basically, that traditional methods would give you this kind of outcome. Whereas if you use generative model-based methods, they can give you much more pleasing results with the same compression ratio. It means you can compress the same file size and still can recover quite nice images. People have been extensively using these GAN-based models, generative models, to do digital artworks. And here I show you on two sides. One on the left is to generate the images. This is award-winning picture that's been generated using AI. And on the right, that's the lyrics written by AI and also music generated by AI. You can click here and go inside. This is the challenge. This particular picture was the winner. And these are the more pictures generated by AI, which are shortlisted. They look quite artistic. And you can see more and more pictures, and you will find all the details of these images within. This is computervisionart.com. These are different set of images, more and more. Since you can hear the audio, I would like to play this particular song, one of the songs. This is again from OpenAI. Let's play.
All you know it's gonna be alright. Let the darkness fade away, and you gotta feel the same. Let the fire burn. Just as long as I ain't there, I'll be there in your life. I'll be there when the emissions rise, and I don't need to call it.
All right, it will keep on going on. They're quite pleasing, I'll say. Yeah, so people are using this thing for the artworks. And not only that, the generative models can be used in processing, having less acquisitions in medical imaging, such as CT scans. CT scan basically work by passing this radiations through the body. This is there is a body, and then there are the detection on the other side, right? And then less the number of the rays that you have, better it is in the, for the health of a person. And then if this is how the normal CT scan would look like, if you have the less number of scans, then this is how the CT scan would look like, which is not that much of a value for the medical use. But using the same amount of data for in terms of the acquisition, one could use generative adversarial models, generative models in general, then can obtain quite nice, as good as the images otherwise, by having much more less number of acquisitions. And these are the works that are currently being done as well. These are the usage in medical imaging, and then these generative models, this time it's been conditioned on the normals, depth, material segmentation, mask, and so on and so forth. You can condition them all together, and they can again train a generator, and then again this adversarial way of training of this particular network essentially becomes a conditional GAN, and that would allow you to have quite realistic quite realistic augmented reality. Here you can see that this is the background, and you can actually place this particular car with a very, very realistic way, where only the top results, top things are the inputs, and then it's been rendered very quite accurately. Yep. So this kind of generative models can be different materials and so on and so forth. So to render the fancy augmented reality. All right. Those are the promises, some of the examples that I showed, which we could, it has been being used, and it's constantly will be better over time. Since it has been so far, there is no reason why it would not continue. Whereas on the side, the dangers of mostly regarding these privacy concerns has also been discussed before, regarding the deepfakes and so on and so forth. That always remains there. So to me, that one of the scariest one, that this particular paper that is published in a major venue from people from Berkeley and Adversarial Research in the University of Michigan, that CNN generated images, often these conditional ones or also non-conditional ones, are surprisingly easy to spot. It means that you can actually still know, even if human cannot do it, the other AI can still do it, but that seems like it's only for now. It means that it's really, really going fast, and we don't know what's going to happen next in regard to even AI may not be able to catch, or humans seem to not to be able to differentiate them in a large extent now already. So that for now thing is what this is the work from the last year, and then things are of course improving more and more, and maybe it will just become so difficult that human will not be able to differentiate, or not even human, AI will not be able to differentiate which one is real and which one is fake, and hence creating this problem of this deep fake, and then spread of this fake news and so on and so forth, based not only based on the images and videos, it could also be based on the text and so on and so forth, and any form of the digital documents. Another examples that you could actually take the audio, and then you can actually lip sync that audio with any video and make the person speak like that. This is that video manipulations, where you take the video from one source and then audio from the other source, and then you try to align them together, and hence make the person say the way that you want to say in a very, very realistic way. This is the other dangers that there's one side is that you can actually replace the face of a person by the other person, but the audio remains the same. Then other is that you could keep everything as much pretty much the same, but you can change what you can just record and then make the other person say whatever you want the person to say. Either that can be commanded in terms of the audio could be the input, and now this is still the conditional GAN in some sense, because you have both the images as an input and audio as an input, and you are getting this image as an output that has been conditioned on both images and the audio. Here is an example of that particular wave to lip. You're basically doing the lip syncing based on the wave, which is the audio. And
hey, Vsauce, ByCloud here. And this video is going to be really weird. Eerily, you might say, but surely it looks unusual. Some of you may have already noticed, but this is not a mere coincidence. And the reality is, and AI is behind what you are seeing right now. It uses my voice to lip sync the face in the video, and what's different to deepfake is that it's using sound instead of another face to generate lips movement. You can read up their official paper called "A Lip Sync Expert is All You Need for Speech to Lip Generation in the Wild," short for wave to lip, if you are interested in the details. But let's just say you can do basically anything related to lips and audio generation, of course. With just an audio clip, you can use it to sync up with the videos of your choice, and just with a quick render, you will get something like what you are seeing right now. In a way, basically dubbing over the video along with the change of lips movement. Isn't that useful? Well, and a bit concerning. Anyways, there are still a lot of functions that we can look forward to. For instance, there's a lecture in a language that you do not understand. With a translated audio dub, you can easily use this AI to lip sync and watch it like they actually speak the language of your choice. The same goes for movie or sports dubbing. It is also as easy, but the quality of this definitely still needs some improvement. In some cases, you can see the blurry mouth shape or the replaced image outline, like this clip I just played. This not only can be helpful for dubbing, but also animate CGI characters. Remember how badly some auto-generated facial expressions and lip syncing in some games can be? Well, this could be one of the potential solutions. Another really interesting implementation is that it can be used to generate cutoff or disrupted video calls while the audio is still going through. It may look a bit creepy though, just only seeing someone's mouth moving. Last but not least,
Okay, because the idea that one can basically condition upon the audio and modify the video so that the person in the video would speak the audio that you supply to.
hey
It's
Vsauce.
not only in the audio, actually you can also feed just the text. You can just write the text and ask the person to speak the audio. Text gets converted into the speech, and speech get lip synced to the video, and hence the person in the video would look like actually reading the text that you have provided. It goes that far. This particular is text to vid. This is the network that's again trained in a conditional GAN manner, and I can show you some of the examples here.
We introduce a practical tool for iteratively editing talking head video. Starting from this video, this was easy for us. We edit the transcript, and within 40 seconds, we obtain this. This was entertaining for us. Because our tool is fast, we can try different wordings. We replace entertaining with hard. This was hard for us. Finally, we decide to just say the job was required. Here we have the actor test different grades for the film Hereditary. I'm going to give Hereditary a B-. The grade is too low, we edit the grade to A+. I'm going to give Hereditary an A+. Happy about the grade, we add a smile at the end. I'm going to give Hereditary an A+. Our tool focuses on video synthesis and can use speech audio from many sources. We've been using a library of the actor's real voice recordings, but we can also use neural voice cloning, or, as in this case, generic text-to-speech. Here we start by making the actor quote a line from the film Jaws.
You are gonna need a bigger boat.
We change the wording a little.
You are gonna need a bigger ship.
After more iterations, we settle on the wording.
You are gonna need a capacious boat.
In this session, we make the actor say lines from crime films, such as,
"Say hello to my new bazooka."
We change the wording to have him channel Al Pacino from as target video. Our tool can still help the editor explore alternative lines. We first try the line,
"I will make him suffer."
For more creepiness, we add a closed-mouthed smile at the end.
"I will make him suffer."
After a few iterations, we settle on a different, less hostile line.
"I will have him pay for what he did."
In this session, we use neural voice cloning for audio, which means both the video and the correct actor's voice are synthesized only from text. We make the actor say an excuse from the film American Psycho. I have to return some videotapes. We change the line to have stronger mouth motions. Here we slow down the video to show the difference. We now go back to full speed.
May the force be with you. May the force be with you.
We have evaluated several aspects of our pipeline, comparing our retargeting to baseline methods.
May the odds be ever in your favor.
Directly copying parameters leads to a rounded mouth that looks unnatural. Linear regression has trouble closing the mouth fully, such as at
I think my mask of sanity is about to slip. I think my mask.
I guess
the tree fails to close
you got
it.
the idea here again that you could control not only giving the audio but also giving the text, and you can control the head pose, you can control the expressions and everything that as you desire, and in a very, very realistic manner. And that's how that deepfake I mean, these are of course not only the bad sides, it of course has a good side that you could actually now make more realistic translation of the dubbing of the movies and so on and so forth. But on the other hand,
we introduce a practical
you
tool
can yourself
for
guess that what kind of dangers it could bring by regulating malicious users to generate videos that speak out things that the user actually, that the person in the video doesn't actually say. So I tried trying one video in, apparently this is like one of the last slides I think I have, and there you go.
जिन्दगीमा एकपल्ट महिला हेरेन भने जुनसुकै विकसित देशको जोसुकै मान्छे होस् जोसुकै धनी होस् गैँडी देखाएको छैन.
So that was the video. Lip syncs are not that perfect yet, but then those could actually most likely be improved. But you can see that you can take the language from the audio from completely different video than video from elsewhere. You can put them together and make it look like as the person in the video actually saying those things from the audio. Those are pretty much the content that I wanted to present, and I didn't discuss much about the bad sides or basically the dangers, so that I still would stay for the open discussion based on the questions that you have. With that, I would like to end my presentation. Thank you very much for your attention, and I will be open to the questions. Thank you.
Thank you, Dandaji. It was really a very wonderful presentation, like about the conditional GAN and the generative adversarial networks. It was very intriguing and very much interesting. Like there are so many things that AI can do, like we cannot even imagine right now. So thank you very, very much for your time. And now we are open to our questions. So I got one question from Bibasji. So Bibasji, you can introduce yourself and just ask him what you are going to ask. Thank you.
Hello, I am Bibas. The question, so I actually do some software developments and a bit of AI, so I'm just a student, let's say. My question was related to the sound clip that you showed, the song actually. So was the voice generated by the model as well, or it was just the text generated? So that was my question.
There are multiple versions. There are also some versions where even the voice, music, lyrics, everything is generated by the AI.
No. So my question was regarding the sound clip that you played.
The sound clip was actually is generated by AI. Even the voice, that particular one, is generated by AI. That's why when you play it, you just don't really sound it.
Stay tonight. Don't you know it's gonna be alright?
Yeah, this is basically generated by AI. Even the sound. Yeah.
So if you have any kind of questions, you please feel free to ask.
Dandaji, this is Uttam. You have shown many pictures and that is made by AI and enhanced by AI, but I haven't seen any sort of graphs. Like, I wonder you can create a scientific chart, chart graphs, or any sort of graphics that is used in scientific publications, and the challenge of regulating those things, even now, the fabrication of data is a huge challenge for the scientific community. And how can we deal with that once, the AI can create, the image or graphs, which is as same or as good as, the real experimental thing that can create. So how can we regulate? What is your take on this thing? Can they produce that sort of graphs? And if so, then how can we, regulate this thing?
So in terms of that's a very good question, first of all. Yeah, so from the scientific point of view, that until the last year, that you could actually have reasonably good accuracy, depending upon what particular settings that you have. You can have more than 90% accuracy of knowing whether it's actually deepfake or it's not, or even more. But the problem is that you could know even with the 99% accuracy, if you have access to those models, and if you don't have access to those models, there could be always some new models that you would be completely unaware of. So it just really becomes this, even the adversary on the adversary. It means that you can have a model that can detect all the existing ones quite well, but there might appear a new one that cannot be. So from the quantification point of view, that this particular paper quantifies very well, showing that it is quite easy for AI to detect whether it's fake or not, whereas it's not easy for people to detect, and that those kind of quantitative evaluations you can find on this particular paper. The thing is that sometimes maybe just having few qualitative very good examples may be damaging enough than just going to the quantitative cases. For example, that I might just try to manipulate 100 different times of your video, then one of them turn out to be good, and that might be sufficient enough. So even if you have 90.9% times not good enough, then one of the, because it's very cheap to generate even those all 100 different varieties, right? So then that's, although that particular thing does not seem to be there in really, especially because that we don't really know that how to quantify them. More about the defects generated by the existing deep models can be, if a new model is trained, can easily detect them. Whereas the problem is there could be a new model that can learn to fool the one that's been just trained to detect. And that's the adversary that takes place on top. And that's what the danger is, that no matter how good models do I train to detect, then I do not have the access to the data generated by those models, which would be there in the future, right? So then it's really about this kind of hacking idea that you can have a perfect model, but then somebody might be able to hack that particular one. And then that's more of a danger, I would say, a bigger danger, I would say. But then if you see the current streamline of what is happening so far, then it seems like it's only going to be improved more and more, and we don't know that how difficult or easy is going to be in future. Yeah, so to have more comprehensive analysis, that one can have look into this particular paper of deepfake detection. Yeah.
Thank you. So we have one more question from the Banji herself. So can you please ask?
Hello, Danda. Firstly, thanks so much as to interesting र इन्फर्मेटिभ प्रेजेन्टेसनको लागि। सो मेरो क्वेसन चाहिँ अब इट्स अ भेरी जेनेरिक क्वेसन होइन। अब जेनेरेटिभ एल्गोरिदम भन्नु बित्तिकै सबैजना दे आर सो क्युरियस होइन, किन कम्प्युटरले सबै गर्नु सक्छ तर जेनेरेट गर्न सक्दैन, क्रिएट गर्न सक्दैन भनिरहेको थियो। अब त्यो पनि भइरहेछ। सो अहिले एकदमै अब आएको यो ज्ञान र GPT-3 छ नि होइन, यो दुईटामा एकदमै फन्डामेन्टल लेभलमा होइन, बेसिक लेभलमा वाट आर द डिफरेन्सेस एन्ड वाट आर द सिमिल्यारिटिज?
So in terms of the architectures, in the implementation, they come in the different streamlines, I would say. So GPT-3 it comes more from this NLP background, and then therefore it's been used using this something called transformers, and the other GANs often, not always, but often most of the times using these convolutional neural networks, and that's what it uses. But the recent GPT, that the one actually I discussed about, the one of the OpenAI that trains, let's say, DALI, this particular one. This is using this GPT-3 model already within, and then eventually that to generate the images, it has to generate in the adversarial manner. And there are two sides. One side is more about that you could not make it adversary, but do in self-supervised manner of the learning, and that is very easy to do in the text settings. Whereas in the image settings, similar kind of removing the text is not that easy, because we don't really know like which one is word, and then this sentence separations cannot be done in the images. And that's principally that's how this the GPT-3, and then let's say more about this scene and based GANs, right? Or image based GANs actually quite differ. But on the other hand, you can see one can be done in self-supervised manner without requiring maybe I'm not really expert in the NLP, so but then maybe NLP can be largely trained using the self-supervised manner by just removing and playing with the words and so on and so forth, and that's where the GPT lies mostly. Whereas these GANs, especially these image GANs, those things cannot be done. Therefore, they have to be heavily rely on adversarial learning, where you have with the generative and discriminator-based learning. But then this is actually two things put together. This particular slide of this DALI from OpenAI, it just puts these two things together so that you could actually describe in the natural languages the images, and it generates images out and there. Actually, these both the things actually been put together. Although the paper is not out, the source code is not out, so we don't know what exactly is there. This is more of the guess and some of the blocks, and this been out there. So that's what we guess, that it puts both of them together. That's the hints. I cannot exactly say the exact differences because of this technology not being out there yet. Yeah.
Yep. Thank you, Dandaji. On this note, we will end our webinar series here. Thank you, Dandaji, for this lovely presentation. It was really amazing to know so many things which we haven't heard before. So thank you for participating, everyone. I hope to see you soon again in the near future.
Thank you everybody for
so
your
much.
attention. Thank you very much, series, for hosting the talk, and yeah, thanks. Yeah, cheers.
Thank you.
Have a nice day, nice evening. Thank you. Bye bye.
Bye.
Thank you everybody. Bye. Bye.
Thank you, Dandaji.
Thank you very much.
Bye bye.